My name is Matthew Hall, and this is lab report number 3 about a black hole. The purpose of this lab is to computationally model the relationship between the mass of a black hole and its net gravitational force on an outside star. The net gravitational force exhibits an orbit, allows the star to move in an orbital fashion around the black hole, and we'll see a difference in speed and momentum as well as a change in the forces, the direction that they are pointed in. Now, in the diagram, we'll see that the net force increases the closer it gets, and it decreases further away. Some important concepts include the momentum principle, which is mass times velocity, and the change in this. And additionally, we'll see some curving motion equations such as F net equals dp over dt, and that net force equals the net force in the parallel component and the perpendicular component. Additionally, we'll use Newton's second law for some black hole calculations. As observed in the model, we said there are 3 forces that act on the star as it moves in its orbital pattern. The blue arrow is a net parallel force, and it changes directions throughout the course of the orbit to show that the star is both speeding up and slowing down. It speeds up the closer it gets to the black hole, and it slows down the further away it gets. That's because of the force of gravity. As the distance between the two gets smaller, the net force gets larger, and it accelerates and moves faster. The pink arrow indicates a perpendicular net force, and this net force is always perpendicular to the green motion of the star. So it doesn't always point towards the center because this is an orbital pattern, but it's always perpendicular, and it does increase over time also because of the force of gravity. And then the total net force is the accumulative combination of the pink force and the blue force. And it's always pointed towards the black hole. And again, that is because of the changes in forces that we see in the blue arrow and the pink arrow. The approximate mass of the black hole is around 1.2 times 10 to the 34th kilograms. And we see that the gravitational force is our standard gravitational force and also the code version of it too. Now, in the code, we see a lot of integration of both the curving motions as time moves on. You see a lot of the dp dt and deltas and all that's all integrated into the code, and we see our relationship between our net force and our perpendicular and parallel forces. Additionally, on the left side, you see that the mass and the time was manipulated in order to track the daytime. In conclusion, we say that there are differences in the net force and the change in momentum. And like I said before, this is attributed to our force of gravity, as for the most part, the distance is the one that is being manipulated, and the closer that we get, the more attraction there is between the two entities. And then this relates a lot to the change in momentum, because as there is net force, there is acceleration, and as the net force decreases and decelerating. So we see that there's the differences in speeds. Now, for the what if question, if you imagine that there is another black hole with a different mass that replaces it, then only in that instance would you be able to tell. But you'd only be able to tell if the orbit is different. According to the what if question, we were to imagine that the orbit remains the same, which you would not be able to accurately tell, because the force of gravity is what would vary the most, which would accelerate and decelerate the star at different rates, which would not allow it to follow the same orbital pattern. Thank you.